My name is Tom Beucler, and I am an assistant project scientist at UC Irvine, affiliated with Columbia University. Today, I will introduce climate-invariant networks, which are physically rescaled neural networks that can generalize to climates they have not been trained on. I would like to thank my co-authors, as well as the organizers of this virtual conference for inviting me today. The primary motivation for this talk is that the largest uncertainties in our long-term climate projections come from clouds. More specifically, models fail at representing the effect of fine-scale cloud and turbulence on climate because most climate models use a coarse grid with empirical models of clouds, which distorts the multi-scale interaction between climate, convection, and clouds. Thanks to computational advances, we are now able to run global simulations with a grid fine enough to explicitly simulate deep cloud systems. However, because of computational limits, we are only able to run such simulations for a short period of time. For instance, only 1 year, which pales in contrast to the 100-year simulation we would need for long-term climate predictions. In parallel to the development of global cloud resolving models, progress in stochastic optimization has improved machine learning algorithms to the point where they can be trained on these high-resolution simulations to accurately mimic the effect of deep cloud systems on climate. To make things more concrete, I will introduce the setup that our lab uses to build machine learning parameterization of convection. The high-resolution model we will learn from is a superparameterized model, which is made of two models that interact at each time step. It has an exterior model that has the typical resolution of a coarse climate model. From a large-scale thermodynamic state at a given time step t, it calculates large-scale heating and moistening tendencies from advection and radiation. What defines superparameterization is the presence of an interior model in each grid cell, which uses a two-dimensional cloud resolving model to produce the response of clouds and convection to given large-scale conditions. The large-scale and subgrid scale tendencies are then summed up to advance the large-scale thermodynamic state from one time step to the next. The role of the neural network is to emulate and replace the interior model, which can make the climate model up to 100 times faster, with minimal accuracy trade-off. To summarize, the neural network, which you can think of as a powerful nonlinear regression tool, maps the large-scale thermodynamic state, that is, large-scale water vapor, temperature, and surface conditions, to how convection and clouds redistribute energy in the vertical in the form of water vapor, temperature, and radiation. Because the problem is high-dimensional, we here use fully connected artificial neural networks and typically use formal hyperparameter tuning to determine the optimal number of layers and nodes. We use 42 million samples from the first simulation year as training data and 42 million samples from the second simulation year as validation data to avoid overfitting. Once the neural network is trained, it can accurately emulate both convective moistening on the left and convective heating on the right from the superparameterized model, where the truth is the top row and the fit the bottom row. Several research groups cited on the very bottom row have already developed prototypes of machine learning parameterizations of subgrid scale thermodynamics for climate modeling. However, we are still in the very early ages of these data-driven parameterizations, and today's talk is motivated by two key issues. First, machine learning algorithms fail to generalize outside of their training set. Here, I am showing a daily average profile sample from the tropics of a reference climate we have trained several neural networks on. These neural networks, which include in orange and green neural networks engineered to conserve mass and energy, all fit the daily mean tropical profile of convective moistening pretty well. However, if you take the same network and evaluate them in the tropics of a warm climate they have never been trained on, all neural networks, including the physical constraint one, make large generalization errors. This is the first central issue we will try to address today. The second issue arises when we take a step back from the modeling world. While the current global observing system can approximate the large-scale thermodynamic state to some extent and inform the development of climate models, the same statement cannot be made for the moistening and heating tendencies resulting from kilometric scale convection in clouds. These are residual quantities that can only be accurately measured via costly and targeted field campaigns, such as the recent Eureka campaign in the Barbados shown here. This implies that we have to work with very sparse and localized data to develop data-driven parameterization of convection, which is challenging. These two problems lead to the central question of this talk. Can we adapt machine learning algorithms to predict out-of-sample climates? By out-of-sample, we are referring to both problems in one question. First, out-of-sample because we may want to predict a climate we never observed. And second, out-of-sample because we may want to predict different regions of the same climates, some of which have sparse observations and some of which don't have observations at all. The talk will have two parts. First, I will show how physical rescalings can help neural networks generalize and introduce the notion of climate-invariant neural networks. And second, I will show that climate-invariant neural networks learn more general mappings from climate to convection with very little data and facilitate transfer learning between idealized and realistic atmospheric data. Note that while I am investigating the specific case of subgrid scale thermodynamic parameterizations for climate modeling, the framework is general enough to be applied to data-driven emulation of, for instance, meteorological or oceanic models. We start by coming back to our first problem. Brute force statistical models tend to make very large errors when evaluated outside of their training set. Our first idea is to break the statistical models even more so that we clearly know which solutions are most promising to make neural networks climate invariant. For that purpose, our generalization experiment will be a uniform 8 Kelvin surface warming experiment. We will train and validate our models on a cold aquaplanet simulation and test these models in the deep tropics of a warm climate, which is clearly outside of the neural network training sets. In our experiments, the surface temperature is prescribed using a realistic equator-to-pole surface temperature decrease. In blue, we show the surface temperature of a cold aquaplanet experiment as a function of latitude. And in red, we show the surface temperature of the warm aquaplanet experiment used to test the generalization property of our machine learning algorithm. As you can see, there's an entire range of latitudes corresponding to the tropics of the warm climate, where we will evaluate the neural network parameterization to surface temperatures it has never been exposed to. So to summarize, a neural network will be trained on the cold climate and tested out of sample in the deep tropics of the warm climate. So first, let's try this new generalization experiment with a brute force neural network. Again, we test the neural network on daily mean data, subgrid moistening to the left and subgrid heating to the right. It does quite well in the reference climate it was trained on, which is important because from the training and validation data in the reference climate alone, you would deem this neural network to be quite a good fit. Now, let's take a tropical mean sample in the warm climate and test that same neural network. And it fails miserably. It fails by more than a factor 10 now that we made the jump between the surface temperatures of both climates as high as 8 Kelvin. So how are we going to proceed? Our goal is to uncover climate-invariant mapping from climate to convection. That is, a single mapping encoded within a neural network that works for both the cold reference climate and the warm climate we are trying to generalize to. What we've seen so far is that a brute force fit is not climate invariant. The goal is to change this mapping to make it climate invariant. And for that purpose, we will borrow the concept of self-similarity from fluid mechanics. That is, if there is some self-similarity between how convection interacts with a large-scale climate in a cold and a warm climate, we should be able to change variables so that the same mapping can be used in both the cold and the warm climate. The question then becomes, how do we choose the right physical rescaling? Most likely, this is an ill-defined question and there is no unique rescaling. However, there is one particularly striking nonlinearity in the climate system that emerges from the Clausius-Clapeyron equation, and that nonlinearity dictates that the saturation water vapor pressure is an approximately exponential function of temperature. In our aquaplanet simulation, this relationship can be seen by averaging the near-surface water vapor concentration on the y-axis, conditioned on the near-surface temperature on the x-axis. As the climate warms, we can see the approximate exponential, which is what makes it so hard for the neural network to extrapolate from a cold to a warm climate. Based on the underlying data, both this orange and this brown errors are reasonable guesses, but both of them would lead to large generalization errors. The trick is then to use this upper bound given exactly by the Clausius-Clapeyron equation to normalize the specific humidity input to the neural network, therefore putting a cap, an upper bound on the extrapolation error. Algorithmically, this can be achieved within the neural network's architecture by using custom data generator and custom layers. Starting from a standard neural network, taking the core scale thermodynamic state as input and the subgrid scale tendencies as outputs, we first physically rescale the inputs by using a custom layer or custom data generator. And then we inverse transform the direct outputs of the neural network so that the machine learning algorithm is emulating the climate-invariant version of the mapping. In practice, implementing this transformation within the neural network is convenient because it allows us to use a single suite of training, validation, and test datasets while testing multiple rescalings by only changing the custom layers without having to regenerate the full datasets over and over again. Thanks to that, we were able to test multiple physical rescalings, and we kept the rescaling that yielded the best generalization result via trial and error. So let's start with the first input, namely the specific humidity profile, which is the water mass concentration. Because of Clausius-Clapeyron, the specific humidity is clearly out of sample in the warm climate compared to the cold one. However, once we normalize the specific humidity by its saturation value, which yields a relative humidity, the two probability density functions almost perfectly align. That is, by changing input variable from specific humidity to relative humidity, we have transformed an extrapolation problem into an interpolation one. And as expected, the ability of the neural network to generalize to the tropics of the warm climate improves drastically after this first physical rescaling. That being said, errors are still large in the lower atmosphere, where the network is exposed to very warm, out-of-sample temperatures, begging the question, can we similarly normalize temperature? A simple scaling that was suggested by Paul Grumman was to subtract the near-surface temperature from the temperature, transforming, again, the extrapolation problem in the lower atmosphere to an interpolation problem. As expected, this improves the generalization skill in the lower atmosphere. However, there is still a problem with the sign of convective heating. Which brings us to the last major input rescaling. As the surface sensible heat flux does not change much with climate, the main culprit is the surface latent heat flux, which we normalize using the saturation specific humidity. Again, we go from extrapolation to almost interpolation by dividing the latent heat flux by surface saturation specific humidity. And that leads to quite reasonable performances given the large 8 Kelvin generalization jump. To summarize what we have done so far, we have physically rescaled the inputs so that the probability density functions of inputs were as aligned as possible across climates. We rescale specific humidity to relative humidity, temperature to temperature minus near surface temperature, and divided latent heat flux by the surface saturation specific humidity to yield climate-invariant neural networks that are able to generalize to unseen climate. Taking a step back, the specific result is consistent with a broader consensus in the literature that using physics to intentionally phrase machine learning mappings can dramatically improve performance, often more so than carefully tuning the algorithm itself. And that underlines how important it is that domain knowledge experts, in this conference that would be the geophysicist, interact with machine learning specialists. For the last part of this talk, I will show advantages that climate-invariant neural networks have over brute force neural networks. First, climate-invariant neural networks learn mapping marginally faster. Plotted is the mean squared error, with up being worse and down being more accurate, as a function of the number of samples that the neural network is trained on. We obtain a statistically significant difference in the limit of small sample size, here 10,000 samples, but then do not notice any clear advantage of the climate-invariant neural network of the brute force neural network, especially as it tends to overfit the training set for 1 million sample in this particular example, where we do not use a validation dataset. However, where climate-invariant neural networks really shine is when we repeat the same curve but evaluate the error on the test set, that is the warm climate from the generalization experiment. With only very little data, it is already able to make predictions on the warm climate that are 2 orders of magnitudes more accurate than the brute force network, suggesting that the climate-invariant network is able to learn a more general representation of subgrid scale thermodynamics. To more formally investigate the sparse observational data problem mentioned in the introduction, we now want to compare how the climate-invariant neural networks differs from its brute force counterpart when it comes to transfer learning. Transfer learning is responsible for a lot of the recent progress of machine learning in research and industry because it circumvents the difficulty of collecting and labeling large amounts of data by connecting 2 tasks. First, a task where training data is easily available and for which we machine learn a model that we have confidence in. Second, a task for which data and labels are sparse, which makes training a model from scratch impossible. In that case, we reuse the model trained for task 1 and adjust it using the sparse data to perform task 2 with reasonable accuracy. In climate sciences, a logical application of transfer learning is to go from climate model data, which can be outputted at arbitrarily high spatiotemporal frequency with perfect labels, to sparse observational data. Ham et al. Recently showed that by training a convolutional neural network on historical simulation, first, before doing transfer learning on the comparatively small observational record, then after, that the seasonal forecast scale of the Niño index 3.4 was improved by a statistically significant amount. This and other lines of evidence suggest that the climate model data contains information that complements the observational record, opening the door to first training a data-driven model on climate model data to then fine-tune it on the observational record. In our case, we can create a numerical laboratory to investigate the amount of data needed to transfer knowledge from idealized to realistic atmospheric data. We train a neural network on aquaplanet data before unfreezing and retraining all of the weights on data coming from a realistic geographic superparameterized simulation. From a machine learning perspective, we are doing inductive transfer learning as we retrain our aquaplanet neural networks on labeled data from a closely related task. Let's start with transfer learning from the aquaplanet to the real geography simulation. The mean squared error is still on the y-axis, while the x-axis is the number of samples used from the real geography dataset to then retrain the aquaplanet neural network so that it can perform well in a realistic setting. Our preliminary results suggest that not only does the climate-invariant network perform better on datasets with different characteristics without any retraining, that is the column to the left, it also needs to be trained on less sample to yield the same level of error as a brute force neural network. This concludes our recent results, and I wanted to share a few future directions we're excited about. First, we're in the process of implementing a Fortran equivalent for the climate-invariant neural network so that we can plug it in operational climate models, which we hope will help stabilize the overall simulation by avoiding the out-of-sample problem. Second, we are experimenting with different physical rescalings for the output and the vertical coordinate in order to more accurately represent the convective heating profile and the general upward shift of the atmosphere with warming. Last but not least, these results ask the questions of how self-similar the interaction between convection and large-scale thermodynamics is across climates. And it would be really interesting to hear your thoughts about possible experiments to run to investigate this topic further. To conclude, we come back to our initial question. Can machine learning algorithms be used to predict out-of-sample climates? First, physical rescalings can convert extrapolation into interpolation and help create climate-invariant neural networks that generalize outside of their training set. Second, we have shown that climate-invariant networks learn more general mapping and generally facilitate transfer learning from idealized to realistic atmospheric data. Taking a step back, the implication of our results are that combining machine learning with physical rescalings lead to machine learning algorithms that are much better at generalizing outside of their training set. Our results additionally suggest that training these more general machine learning algorithms on model data and adjusting their weights on sparse realistic data can result in machine learning algorithms that are both general and realistic. What I find really exciting is that our results suggest that physics-guided machine learning may be a useful tool to assist and complement modern data assimilation to assimilate campaign data into uncertain components of global climate models. For instance, when it comes to tricky variables like convective heating and moistening. And with that, thank you all for attending this virtual conference, and please visit my website if you're interested in the papers or the codes corresponding to today's presentation. Thank you.